Think of an elephant. You already know what it is supposed to look like. The same goes for a bird, a shark, or almost any animal you have seen before. Now imagine finding one with a body part that seems to belong to something else entirely. The fossil record is full of creatures like this, and the strangest part is that many of these bizarre designs worked for millions of years before disappearing. Platybelodon is a good place to begin because almost everything about it looks familiar. It belonged to the Proboscidean family tree, the larger group that includes modern elephants. It had a trunk, thick column-like legs, a massive body, and tusks. From a distance, you would probably recognize what kind of animal you were looking at. Then it would turn its head. Its lower jaw projected far beyond the mouth, and at the front sat two broad, flattened lower tusks. Together, they formed a wide cutting edge, unlike anything carried by a living elephant. The resemblance to a shovel was so obvious that early reconstructions often placed Platybelodon in wetlands, supposedly scooping soft vegetation from mud and shallow water. The fossils eventually complicated that picture. Tusks preserve microscopic damage produced by repeated use. When researchers examined Platybelodon specimens, they found scratches and polished surfaces that were difficult to explain through simple digging. Different wear patterns suggest the lower tusks regularly contacted vegetation, including material tough enough to leave directional marks across their surfaces. That makes the feeding scene much more active. Imagine the trunk pulling a branch or bundle of vegetation into position while the broad, lower tusks press against it. Instead of scooping food from the ground, the animal could use the flattened edges during cutting, scraping, or stripping. A structure that looks almost comically oversized in a reconstruction becomes much easier to understand once you see what repeatedly touched it. The jaw also came with a cost. Extending that much bone and tooth in front of the skull created a highly specialized feeding apparatus that only made sense while the foods and environments rewarding that specialization remained available. Modern elephants went in a different direction, relying far more heavily on the trunk and conventional tusks, while the extreme lower jaw disappeared. And Platybelodon was far from the only proboscidean to experiment with this basic equipment. Across their evolutionary history, different branches produced lower tusks, upper tusks, elongated jaws, shortened jaws, and combinations that would look completely out of place on an elephant today. That matters because modern animals can make surviving designs feel inevitable.
An elephant looks correct because every elephant we have ever seen shares roughly the same recognizable blueprint.
The fossil record preserves all the alternatives that no longer stand beside them. Platybelodon altered a pair of tusks until they became a specialized feeding tool. Another animal pushed the same raw material much further. Its teeth did not simply grow larger or flatter. They curled inward until an entire tooth row became a spiral. A fossil sits on a table. It is a tight spiral of backward curving teeth, with smaller teeth packed toward the center and larger ones around the outside. Paleontologists could identify the teeth, but for more than a century, they could not agree on one basic question. Where on Helicoprion's body did this spiral actually belong? The main problem was preservation. Helicoprion had a largely cartilaginous skeleton, so most fossils preserved the tooth whorl with almost none of the surrounding jaw. At different times, researchers placed the spiral in positions ranging from an exposed structure near the mouth to a feature built directly into the jaw. One specimen finally preserved what the isolated spirals did not. Around the teeth were remains of jaw cartilage. When researchers scanned that fossil in 3 dimensions, the whorl appeared along the midline of the lower jaw and occupied almost the entire mandibular arch. The spiral was not hanging outside the mouth. It was built into it. That solved its position, but created a different problem. How could a normal tooth row become something like this? Helicoprion continually produced new teeth, but instead of simply losing the older ones, it retained them. New teeth formed toward the rear of the functional row and gradually displaced earlier teeth inward. As this continued throughout the animal's life, the row curled into itself and produced the spiral preserved in fossils. Some known whorls contain more than 150 teeth. The structure looks like a circular saw. The movement came from the jaw itself. As Helicoprion closed its mouth, the exposed part of the whorl swept upward and backward. That motion also gives us a clue about what Helicoprion may have been eating. Despite its appearance, the tooth whorl was probably not designed primarily for crushing heavily armored prey. Biomechanical models fit better with soft-bodied animals that could be gripped, sliced, and pulled inward. Squid-like cephalopods would have been much easier to process than prey protected by a thick shell. The strangest part is that this weapon grew through a process other animals normally use simply to replace worn teeth. Helicoprion kept the older generations inside the jaw while adding new ones, gradually building a structure that became larger as the animal aged. And even the familiar label of an ancient shark is slightly misleading. Details of the jaw place Helicoprion among stem holocephalans, on the evolutionary branch represented today by chimeras and ratfish. Living chimeras process food with broad tooth plates rather than rows of replaceable teeth. Nothing alive in that lineage carries anything resembling Helicoprion's spiral. Platybelodon used modified tusks to process plants. Helicoprion used a growing spiral of teeth to capture and cut soft prey. The next animal took teeth in the opposite direction. Instead of making them better at cutting, it made them so thin and numerous that the mouth became a filter. And that mouth belonged to an animal flying above the water. A pterosaur crosses a prehistoric lake and drops toward the shoreline. Its wings fold, its feet reach the shallow water, and from a distance, there is nothing especially difficult to recognize. Then the animal lowers its head. The lower jaw of Pterodaustro was packed with hundreds of extremely thin teeth, and in large individuals, the total number could approach 1,000. Some reached several centimeters in length. Placed side by side, they formed a dense fringe that looked more like the bristles of a brush than the mouth of a flying reptile. Microscopic examination shows that these filaments really were teeth, complete with dental tissues. But their shape left little opportunity for the usual jobs of puncturing or tearing. They were long, narrow, and packed so tightly that the gaps between neighboring teeth could be only a fraction of a millimeter. That spacing explains what happened when the jaw entered the water. Small organisms and water could enter the mouth together, but the finest material was caught against the lower dental fringe, while water escaped through the gaps. Pterodaustro did not need to seize one animal at a time. Its food could arrive as hundreds of tiny particles suspended in a mouthful of water. The obvious comparison is a flamingo, although the two animals reached the same basic result with different equipment. Flamingos use specialized structures along the bill and movements of the tongue to filter their food. Pterodaustro relied on an extraordinary lower tooth row, while much smaller teeth in the upper jaw likely helped handle material collected by the filter. This feeding method only works when the mesh matches the food. In Pterodaustro, the unusually narrow spacing suggests that very small aquatic organisms could become a reliable food source. There was a trade-off visible directly in the teeth. A broad, pointed tooth can tolerate forces from biting and gripping. A filament several centimeters long is much more specialized. Once nearly 1,000 teeth are committed to building a filter, the mouth becomes extremely effective at one style of feeding and considerably worse at behaving like the jaws of most other pterosaurs. Its skeleton provides another clue about where that feeding happened. Pterodaustro had relatively robust hind limbs, consistent with an animal capable of spending time standing and moving in shallow water, rather than collecting every meal while airborne. A creature built for flight was repeatedly bringing one of the strangest mouths in pterosaur history down to the surface of a lake. And this is where the animals we have seen so far are still relatively easy to understand. You can still look at each one and immediately tell which side is supposed to face the ground. Paleontologists could not do that with Hallucigenia. Its first major reconstruction placed the defensive spines underneath the body and treated the structures it actually walked on as tentacles growing from its back. The mistake was understandable. Hallucigenia fossils are only a few centimeters long and were flattened into rock more than 500 million years ago. With no obvious modern animal for comparison, even deciding which structures were legs became difficult. Fossils discovered in China provided the answer. In 1991, the reconstruction was flipped. The soft appendages became walking legs, while the rigid structures above them became defensive spines. Later preparations showed that the legs occurred in pairs and ended in tiny claws. But the orientation was not the only thing paleontologists had wrong. A swollen structure at one end of several specimens had been interpreted as the head. It was probably material forced from the body during decay. The actual head was at the opposite end, with a pair of simple eyes and a small mouth surrounded by hardened elements. Farther inside, the throat contained rows of needle-like teeth. The claws provided another clue. Their microscopic structure resembles structures found in living velvet worms, helping place Hallucigenia near the early history of the Onychophoran lineage. Its living connections were simply hidden beneath more than 500 million years of anatomical change. With Yi Qi, the body is easier to read. The surprise begins when you reach the arms. Yi was a small feathered theropod dinosaur that lived roughly 160 million years ago. Its hands carried elongated fingers, but the fossil also preserved something no dinosaur had previously been known to possess: a long rod extended from the wrist. Traces of soft tissue indicate that this rod helped support a membrane across part of the forelimb. Yi therefore combined feathers with a broad sheet of skin, creating an aerodynamic surface very different from the wings of birds. Then, Ambopteryx, another Scansoriopterygid, was discovered with a similar wrist rod and evidence of membrane tissue. This was not a deformity unique to one fossil. A small branch of dinosaurs had developed this kind of wing. It is tempting to call it a bat wing, but bats support their membranes with enormously elongated fingers. Yi used a different arrangement, with part of the membrane supported by the additional rod projecting from the wrist. No living flying vertebrate uses exactly the same system. The important question is whether it worked. Aerodynamic modeling suggests that Yi and Ambopteryx were probably capable of gliding, but powered flight would have been extremely difficult. Their wings performed worse in gliding than the feathered systems appearing in other small dinosaurs, and successful launches may have required greater height or speed. Turning also appears to have been limited. Imagine two different experiments taking place among small dinosaurs. One lineage increasingly relies on long aerodynamic feathers. Another stretches a membrane across a reinforced forelimb. Both can get an animal into the air. Only one leaves descendants still flying above us. Feathered wings survived and eventually filled the sky with birds. The membranous wings of Scansoriopterygids disappeared with the animals that carried them. The final creature did not need wings. Its experiment was concentrated in the skull. When Dunkleosteus opened its mouth, there were no normal rows of teeth waiting inside. The bones of the jaws themselves formed the blades. Dunkleosteus did not need rows of replaceable teeth. The front of its jaws ended in sharpened, bony plates that met like blades. As the animal fed, those edges wore against each other, helping maintain cutting surfaces capable of slicing through flesh and other tough material. But the blades were only one part of the system. The skull of Dunkleosteus was built from several movable elements connected by joints and muscles. When the mouth opened, those parts moved together through a 4-bar linkage, allowing the jaws to reach a wide gape extremely quickly. Biomechanical models suggest that a large Dunkleosteus could open its mouth in roughly 20 milliseconds, faster than the blink of a human eye. That rapid expansion also pulled water inward, potentially drawing nearby prey toward the cutting plates. Then, the same skull switched from speed to force. Powerful muscles drove the jaw plates together, with forces reaching several thousand newtons in large individuals. But the number alone misses the important part. Much of that force was concentrated along narrow cutting edges, allowing the jaws to slice rather than simply crush. This machinery was built into the armored skull of a placoderm, a group of fishes whose heads and front bodies were covered by heavy, bony plates. In Dunkleosteus, parts of that armor were incorporated into a highly mobile feeding apparatus. A structure associated with protection had become part of the weapon. Then, placoderms disappeared during the end Devonian extinction. Nothing alive inherited this exact feeding system. The same is true for the tooth spiral of Helicoprion, the dental filter of Pterodaustro, and the membrane-supported wing of Yi Chi. It is tempting to look at animals like these and see failed experiments. But extinction does not tell us that a body design never worked. Platybelodon used its strange lower tusks for millions of years. Helicoprion persisted with a dental system unlike anything alive today. Pterodaustro fed successfully with a mouth that looks almost unusable to modern eyes. These animals disappeared, but their disappearance happened long after their unusual anatomy had already proved capable of keeping them alive. The animals still living today define what we call normal, and every extinct alternative is judged against them. An elephant looks correct because shovel-jawed proboscideans are gone. A bird wing looks inevitable because the membrane-supported wings of Scansoriopterigids disappeared. Hallucigenia seems almost impossible because nothing walking around today carries the same combination of legs, spines, and body proportions. Evolution never knew which of those branches we would eventually be here to see. Imagine placing all 6 animals beside their living relatives. An elephant relative with a broad blade projecting from its lower jaw. A marine predator carrying a spiral of teeth inside its mouth. A flying reptile filtering water through hundreds of dental bristles. A tiny animal whose legs were once mistaken for structures growing from its back. A feathered dinosaur supported by a membranous wing unlike anything flying today. And an armored fish with cutting plates built directly into its skull. They look absurd because their worlds are gone. If a different set of branches had survived, the strange animals might not be the ones in the fossil record. They might be the ones watching it.